13.8 billion years ago, everything we observe in the universe today existed in a state so incomprehensibly dense and hot that our current understanding of physics simply breaks down. But what we're about to explore challenges the very notion that this moment represents an absolute beginning. We're venturing into the scientific frontiers that probe deeper than the Big Bang itself, examining theories that suggest our cosmic origin story might be far more complex than we ever imagined. In the next hour, we'll journey through cutting-edge cosmology, quantum mechanics, and theoretical physics to explore what might have existed before space and time as we know them began. We'll examine the scientific evidence for multiple universes, cyclic cosmologies, and quantum origins that paint a picture of reality far stranger and more magnificent than traditional origin stories suggest. If you're ready to explore the deepest questions in modern physics, we're about to venture into territories where the very concepts of beginning and ending lose their conventional meaning. Standing at the edge of our understanding, we encounter what cosmologists call the Planck epoch, the earliest period in cosmic history that we can meaningfully discuss with current physics. At 10 to the minus 43 seconds after the Big Bang, we hit what's known as the Planck time, a fundamental barrier beyond which our theories of gravity and quantum mechanics become incompatible. This isn't simply a limitation of measurement or technology, it's a fundamental breakdown in our mathematical description of reality itself. Einstein's general relativity, which describes space-time and gravity with extraordinary precision throughout the observable universe, begins producing infinite values when applied to conditions this extreme. Similarly, quantum field theory, our most successful description of particle physics, cannot be reconciled with general relativity at these scales. The Planck epoch represents a period where the universe was so small, dense and energetic that the very fabric of space-time was fluctuating wildly at the quantum level. To understand these conditions, consider that during the Planck epoch, the entire observable universe was smaller than a proton, with temperatures reaching 10 to the 32nd Kelvin and densities of 10 to the 93rd grams per cubic centimeter. Under these conditions, all four fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces were unified into a single superforce. The distinction between matter and energy, space and time, even cause and effect, may have been meaningless concepts. Physicists describe this state as a quantum foam, where the geometry of space-time itself was constantly fluctuating, creating and destroying tiny wormholes, bubbles, and connections at scales billions of times smaller than atomic nuclei. Current physics cannot penetrate this barrier without a theory of quantum gravity, which remains one of the most sought-after goals in theoretical physics. String theory, loop quantum gravity, and other approaches attempt to provide this unified framework, but none have yet achieved the experimental verification necessary to claim definitive success. What we do know is that during the Planck epoch, the classical concept of time may not have existed as we understand it. Time itself might have been quantized, existing in discrete chunks rather than flowing continuously. The very notion of asking what came before this epoch may be as meaningless as asking what's north of the North Pole. However, this fundamental barrier doesn't prevent us from developing theoretical frameworks that might apply to pre-Big Bang scenarios. These theories, while speculative, are grounded in our best understanding of quantum mechanics and general relativity. They suggest that the Big Bang might not have been a beginning from nothing, but rather a transition from a previous state of existence that we're only beginning to comprehend. The mathematics underlying these theories often point to possibilities that stretch our conceptual understanding to its limits, suggesting that reality itself might be far stranger and more complex than our everyday experience suggests. The space around you appears empty, but modern physics reveals that what we call empty space is actually teeming with activity at the quantum level. The quantum vacuum isn't truly empty, it's filled with quantum fields that are constantly fluctuating, creating pairs of virtual particles that pop into existence and annihilate each other in timeframes so brief that they seem to borrow energy from the future and return it before the universe's accounting system notices. These aren't philosophical speculations, but measurable physical phenomena with real observable consequences. The Casimir effect demonstrates this quantum vacuum energy experimentally. When two metal plates are placed extremely close together in a vacuum, they experience a measurable attractive force due to the different quantum fluctuations between the plates versus outside them. This effect has been precisely measured and forms the basis for certain types of microelectromechanical systems. The vacuum fluctuations are also responsible for the Lamb shift in hydrogen atoms, a tiny but measurable change in electron energy levels that arises from the electron's interaction with virtual photons in the quantum vacuum. These virtual particles aren't just theoretical constructs, they contribute to every fundamental process in nature. The magnetic moment of the electron, measured to 13 decimal places and representing one of physics' most precise experimental confirmations, depends critically on the electron's interactions with virtual particles. Without these quantum vacuum effects, atoms couldn't exist in their current form, chemistry would be impossible, and the universe as we know it wouldn't function. But here's where quantum vacuum theory becomes relevant to cosmology. If virtual particles can pop into existence from apparently nothing, borrowing energy from the quantum vacuum, what prevents this same process from operating on much larger scales? Some theoretical models suggest that our entire universe might have begun as a quantum fluctuation in a pre-existing quantum vacuum. Unlike the virtual particles we observe, which quickly annihilate and return their borrowed energy, this cosmic quantum fluctuation might have grown exponentially through a process called cosmic inflation, becoming permanent and evolving into the universe we observe today. This possibility is supported by calculations showing that the total energy content of the universe, including both positive energy and matter and negative gravitational potential energy, appears to sum to zero. From an energy accounting perspective, creating our universe from nothing doesn't violate conservation laws if the positive and negative energies balance exactly. This remarkable coincidence suggests that universes might be naturally occurring quantum fluctuations in an eternal quantum vacuum, with no net energy cost for their creation. The implications extend far beyond our single universe. If quantum fluctuations can create one universe, they should be creating others constantly. The same quantum vacuum that produces virtual particles around us might be producing entire universes in regions of space and time that we cannot access or observe. This quantum origin model provides a natural mechanism for universe creation that requires no external agent or cause, just the fundamental properties of quantum mechanics operating on cosmological scales. Cosmic inflation represents one of modern cosmology's most successful theoretical frameworks, explaining several otherwise puzzling features of our observable universe while simultaneously opening the door to extraordinary possibilities about reality's true scope. The inflationary model proposes that during the first 10 to the negative 32nd seconds after the Big Bang, space itself expanded exponentially, growing by a factor of at least 10 to the 26th power in less than a trillionth of a second. This expansion was far faster than the speed of light, but this doesn't violate relativity because it was space itself that was expanding, not objects moving through space. Inflation explains why the cosmic microwave background radiation appears almost perfectly uniform in temperature across the entire sky, even though widely separated regions of space could never have been in causal contact after the Big Bang without inflation. It also explains why the geometry of space appears flat rather than curved, as inflation would stretch any initial curvature to undetectably small levels. Most remarkably, inflation provides a mechanism for generating the tiny density fluctuations that eventually grew into galaxies and large-scale structure, with quantum fluctuations during inflation being stretched to cosmic scales. However, inflation theory leads to profound implications about the broader nature of reality. Most models of inflation don't predict that the process stops everywhere simultaneously. Instead, they suggest eternal inflation, where inflation continues in most regions while stopping randomly in small pockets that become observable universes like ours. This process creates a vast multiverse structure with an infinite number of pocket universes embedded in an eternally inflating space-time. Each pocket universe would have its own Big Bang as inflation ended in that region, creating space and time as experienced by observers within that universe. These pocket universes would be causally disconnected from each other, existing in separate regions of the eternally inflating space. The physical constants, particle masses, and even the effective dimensionality of space might vary between different pocket universes, determined by how the quantum fields settled into their lowest energy states as inflation ended in each region. The mathematical models underlying eternal inflation are remarkably robust, emerging naturally from most detailed inflation theories when quantum effects are properly included. The process appears to be genuinely eternal, having no beginning or end, with new pocket universes constantly forming as quantum fluctuations randomly cause inflation to end in different regions. This suggests that asking what came before the Big Bang might be the wrong question, as our Big Bang would simply be one event in an eternally ongoing process that has no ultimate beginning. Some versions of eternal inflation go even further, suggesting that every possible variation of physical laws and constants occurs somewhere in the multiverse. This would mean that there are universes with different numbers of dimensions, different fundamental particles, and even different logical structures governing cause and effect. The vast majority of these universes would be unable to support complexity or life as we understand it. But among the infinite possibilities, every possible form of existence would occur somewhere. Recent observational cosmology has provided significant support for basic inflation theory through precise measurements of the cosmic microwave background by satellites like WMAP and Planck. These observations confirm inflation's specific predictions about the spectrum of density fluctuations and the geometry of space. While we cannot directly observe other pocket universes, the success of inflation theory in explaining our universe's properties lends credibility to its broader implications about the multiverse structure of reality. Rather than beginning with a Big Bang, our universe might be the latest iteration in an endless cycle of expansion, contraction, and rebirth that has been occurring for eternity. Cyclic cosmological models propose that what we call the Big Bang was actually a big bounce, a transition from a previous contracting phase to our current expanding phase, with this cycle potentially repeating infinitely into both the past and future. The ekpyrotic scenario, developed by physicists including Paul Steinhardt and Neil Turok, provides one detailed framework for cyclic cosmology. In this model, our three-dimensional universe is a brane, a membrane-like surface embedded in higher dimensional space. The cycle begins when two branes collide in this higher dimensional realm, releasing enormous amounts of energy that we observe as the Big Bang. The collision doesn't destroy the branes, but causes them to bounce apart, with the energy of impact creating matter, radiation, and the expanding space-time we observe. During each cycle, the universe expands for hundreds of billions of years, with matter and energy becoming increasingly diluted as space stretches. Eventually, the expansion slows due to gravitational attraction, then reverses into a contracting phase. As the universe contracts, matter and energy become increasingly concentrated until conditions approach those of the initial Big Bang, leading to another bounce and the beginning of a new cycle. This model elegantly solves several problems that plague standard Big Bang cosmology. It explains the universe's flatness and homogeneity without requiring the extreme fine-tuning of inflation theory. The approaching Brane collision naturally creates the uniform conditions we observe, as any irregularities from the previous cycle get smoothed out during the contraction and bounce process. The model also eliminates the uncomfortable question of what caused the Big Bang, as there was no ultimate beginning, just an eternal succession of cycles. Each cycle in these models typically lasts about 1 trillion years, making our current universe, at 13.8 billion years old, relatively young in cosmic terms. We have hundreds of billions of years left before expansion stops and contraction begins. During this time, stars will form and die, black holes will grow and evaporate, and complexity will rise and fall countless times before the current cycle ends. Recent observations of our universe's accelerating expansion, driven by dark energy, initially seemed to rule out cyclic models that required eventual contraction. However, theorists have developed more sophisticated versions where dark energy's properties change over cosmic timescales. In these models, dark energy currently drives acceleration, but will eventually reverse its effect, causing space to contract and leading to the next big crunch and subsequent Big Bang. Some cyclic models suggest that information or structure from previous cycles might survive the bounce process, potentially allowing each cycle to build upon the achievements of its predecessors. Advanced civilizations might find ways to encode information in the universe's fundamental structure, creating cosmic libraries that persist through multiple cycles. This could lead to a kind of cosmic evolution, where each universe generation is more sophisticated than the last. The cyclic approach also provides a natural explanation for why the universe appears fine-tuned for complexity and life. Rather than requiring a designer or invoking the anthropic principle across infinite parallel universes, cyclic models suggest that universe parameters naturally evolve toward values that support complexity through a cosmic selection process operating across multiple cycles. Our familiar 3 dimensions of space and 1 dimension of time might represent only a small fraction of reality's true structure. String theory, which attempts to unify gravity with quantum mechanics, requires space to have additional dimensions beyond the 4 we directly experience. These extra dimensions aren't merely mathematical abstractions, but could have profound implications for understanding cosmic origins and the nature of existence itself. In string theory's most developed versions, space-time has 11 dimensions total, 7 more than we observe. These extra dimensions are thought to be compactified, curled up so tightly at every point in our 3-dimensional space that they remain undetectable to our senses and instruments. The precise shape and size of these hidden dimensions determine the fundamental properties of particles and forces in our observable universe, including particle masses, force strengths, and the number of particle species. Brane cosmology extends this dimensional framework to cosmological scales, proposing that our entire 3-dimensional universe exists as a brane, a membrane-like surface floating in higher dimensional space called the bulk. This bulk space might contain other branes hosting their own universes with potentially different physical laws and properties. These parallel universes could exist just millimeters away from us in the extra dimensions while remaining completely inaccessible through normal 3-dimensional travel. The collision between branes in higher dimensional space provides an alternative to inflation for explaining cosmic origins. When 2 branes collide in the bulk, the impact releases energy that appears as a Big Bang from the perspective of observers confined to either brane. This collision doesn't create new space and time, but rather heats up and energizes the existing brane structure, causing it to expand rapidly in its 3-dimensional extent. This brane collision model naturally explains several features of our universe that require fine-tuning in other scenarios. The collision process automatically creates the uniform temperature and density conditions we observe in the cosmic microwave background without requiring faster-than-light inflation. The model also predicts specific patterns of gravitational waves that might be detectable by future experiments. Recent developments in string theory suggest that the extra dimensions might not be static, but could evolve over cosmic timescales. Some models propose that our universe began with all dimensions the same size, but as the cosmos evolved, 3 dimensions grew large while the others remained microscopic. Alternative scenarios suggest that additional dimensions might gradually unfold as the universe ages, potentially leading to dramatic changes in physics and the nature of reality itself. The landscape of string theory encompasses an enormous number of possible configurations for the extra dimensions, potentially 10 to the power of 500 or more distinct possibilities. Each configuration would correspond to a universe with different physical laws, particle properties, and fundamental constants. If all these possibilities are realized somewhere in a higher dimensional multiverse, it would dwarf even the parallel universes suggested by eternal inflation. Experimental tests of extra dimensions remain challenging but not impossible. Particle accelerator experiments search for signs of extra dimensions through processes that could allow particles to escape into the bulk space, or through modifications to gravity at very small scales. Gravitational wave detectors might eventually observe signals from parallel branes or detect modifications to general relativity caused by gravitational interactions with extra dimensions. The possibility of communication with parallel branes represents one of the most speculative but intriguing aspects of higher dimensional cosmology. Gravity appears to propagate through all dimensions, potentially allowing advanced civilizations to modulate gravitational waves as signals that could cross dimensional barriers. Such communications might already exist in the form of subtle patterns in cosmic gravitational wave backgrounds that we haven't yet learned to decode. Reality as we experience it might be fundamentally holographic, with all the information describing our 3-dimensional universe encoded on a distant 2-dimensional surface. This radical proposal emerged from studies of black hole physics, but has evolved into one of the most profound ideas in modern theoretical physics, suggesting that spatial dimensions themselves might be emergent properties rather than fundamental features of reality. The holographic principle originated with the work of Gerard T. Hooft and Leonard Susskind in attempting to resolve the black hole information paradox. When matter falls into a black hole, it appears to be destroyed, violating quantum mechanics' fundamental requirement that information be conserved. The resolution came from realizing that the information never actually falls into the black hole, but gets encoded on its 2-dimensional event horizon surface. Much like a hologram encodes 3-dimensional information on a flat surface. Juan Maldacena's ADS/CFT correspondence provided the first concrete mathematical realization of the holographic principle, demonstrating that a gravitational theory in 5-dimensional anti-de Sitter space is exactly equivalent to a quantum field theory on the 4-dimensional boundary of that space. This equivalence isn't just an approximation or analogy, but a precise mathematical duality, where every calculation in the gravitational theory has a corresponding calculation in the boundary field theory that yields identical results. Applied to cosmology, the holographic principle suggests that our entire observable universe, with all its galaxies, stars, planets, and complexity, might be information patterns encoded on a cosmic horizon located at the boundary of our observable space. We experience 3 spatial dimensions because that's how the holographic information is processed and reconstructed, but the fundamental reality exists as quantum information on the distant boundary surface. This holographic perspective offers new insights into the nature of space-time itself. Rather than space being fundamental, it might emerge from quantum entanglement patterns between different regions of the boundary information. Distance in our 3-dimensional experience would correspond to the degree of quantum entanglement between boundary regions, with strongly entangled regions appearing close together and weakly entangled regions appearing far apart. The implications for cosmic origins are profound. The Big Bang would represent the moment when information processing began on the cosmic boundary, transforming static boundary data into the dynamic, evolving holographic projection we experience as space-time. Before this moment, the boundary information might have existed in some dormant state, containing the potential for our reality, but not yet generating the experience of three-dimensional space and time. Recent work by physicists, including Mark van Ramsdonk and Shinsei Ryu, has shown that quantum error correction plays a crucial role in holographic systems. The holographic encoding naturally includes redundancy that protects information from corruption, much like error-correcting codes in computer systems. This suggests that reality's holographic structure might be remarkably stable and resistant to disruption, ensuring that information about cosmic history is preserved even under extreme conditions. The holographic principle also provides new perspectives on consciousness and observation. If physical reality emerges from information processing on the cosmic boundary, consciousness might represent a particularly sophisticated form of information integration that naturally arises in complex holographic systems. From this perspective, conscious observers aren't separate from the holographic projection, but are themselves patterns in the boundary information that have achieved self-awareness. Experimental tests of holographic cosmology remain challenging, but are being actively pursued. Some models predict subtle modifications to gravitational wave propagation that might be detectable by advanced interferometer experiments. Others suggest specific signatures in the cosmic microwave background radiation that could distinguish holographic cosmology from other theoretical frameworks. The relationship between consciousness and quantum mechanics remains one of physics' most profound unsolved puzzles, with implications that extend far beyond laboratory experiments to questions about the nature of reality itself and the role of observers in cosmic evolution. While early interpretations of quantum mechanics suggested that conscious observation might play a fundamental role in determining physical outcomes, modern understanding reveals a more subtle but equally remarkable picture of how awareness might interact with the fundamental structures of reality. Quantum mechanics demonstrates that physical systems can exist in superposition states, where particles simultaneously possess multiple contradictory properties until measurement forces them to exhibit definite values. The double-slit experiment exemplifies this behavior. Individual electrons or photons create interference patterns when unobserved, indicating they pass through multiple slits simultaneously, but behave like localized particles when detectors monitor their paths. This isn't simply a limitation of our measurement capabilities, but appears to be a fundamental feature of how reality operates at its deepest levels. The measurement problem in quantum mechanics asks how and why quantum superpositions collapse into definite states upon observation. Various interpretations provide different answers, from the Copenhagen interpretation's emphasis on measurement-induced collapse to the many worlds interpretation's assertion that all possible outcomes occur in parallel branches of reality. The decoherence theory explains how quantum systems lose their superposition properties through interaction with their environment, without requiring conscious observers to play a special role. Yet questions remain about why we experience one particular outcome rather than others, and what role, if any, consciousness plays in this selection process. However, recent discoveries in quantum biology suggest that biological systems, including those that might support consciousness, can maintain quantum coherence under conditions previously thought impossible. Photosynthesis in plants achieves near-perfect efficiency, partly through quantum coherence, effects that allow energy to explore multiple pathways simultaneously before selecting the most efficient route. Bird navigation appears to rely on quantum entanglement in certain proteins that allows them to sense magnetic fields with extraordinary precision. These discoveries demonstrate that quantum effects aren't limited to sterile laboratory conditions, but operate within the warm, noisy environment of living systems. Some researchers propose that consciousness itself might emerge from quantum processes in the brain, particularly in microtubules within neurons. The orchestrated objective reduction theory, developed by Roger Penrose and Stuart Hameroff, suggests that consciousness arises from quantum computations in these cellular structures, with subjective experience corresponding to moments when quantum superpositions collapse through gravitational effects. While controversial and not widely accepted by mainstream neuroscience, this approach attempts to explain consciousness's unity and apparent non-locality through quantum mechanical principles. The theory suggests that consciousness doesn't emerge from classical neural networks alone, but requires quantum processes that integrate information across the brain in ways that classical physics cannot explain. If consciousness involves quantum processes, it might participate in the fundamental mechanisms that determine reality's structure. Rather than simply observing a pre-existing universe, conscious beings might play an active role in selecting which possible realities become actualized through quantum measurement effects. This doesn't require mystical or supernatural mechanisms, just the possibility that biological systems can influence quantum processes through their physical interactions with the environment. The act of conscious observation might literally help determine which branch of quantum possibility becomes the realized reality we experience. The implications for cosmic origins are intriguing and far-reaching. If consciousness can influence quantum processes, and if the universe's initial conditions were determined by quantum mechanical events, then the emergence of consciousness might retroactively influence the cosmic parameters that allowed life to evolve. This creates a kind of participatory universe where the future evolution of consciousness helps determine the past conditions that made consciousness possible. The anthropic principle would then become not just an observational selection effect, but an active process where conscious beings participate in selecting the cosmic history that led to their existence. Consider the possibility that quantum measurement effects could operate across vast scales of space and time. If consciousness emerged in our universe and learned to manipulate quantum processes directly, it might influence quantum events throughout cosmic history, including the quantum fluctuations that occurred during cosmic inflation. These influences could help explain why the universe appears so perfectly fine-tuned for complexity and consciousness, not through random chance or divine intervention, but through a kind of quantum bootstrap process where consciousness helps create the conditions for its own emergence. Advanced forms of consciousness might develop capabilities that seem impossible from our current perspective. Future civilizations might learn to manipulate their own quantum states directly, accessing information from quantum superpositions or influencing physical processes through quantum measurement effects. Such capabilities could blur the traditional boundaries between mind and matter, observer and observed. These post-biological intelligences might exist as coherent quantum systems capable of maintaining superposition states while remaining conscious, effectively existing in multiple realities simultaneously until they choose which possibilities to actualize. The consciousness cosmology connection also raises questions about the relationship between individual minds and cosmic scale processes. If quantum entanglement can connect distant parts of the universe, and if consciousness involves quantum processes, then individual minds might be more connected to the cosmos and to each other than classical physics suggests. The boundaries between different conscious beings and between consciousness and the universe itself might be less distinct than our everyday experience indicates. We might all be aspects of a single cosmic consciousness experiencing itself from multiple perspectives, connected through quantum entanglement effects that operate beneath the threshold of ordinary awareness. Some theories suggest that consciousness might be fundamental rather than emergent, existing as a basic feature of reality alongside space, time, and matter. In this panpsychist view, all quantum systems possess some primitive form of consciousness, with complex awareness emerging when these basic conscious elements become sufficiently integrated and organized. This would mean that consciousness has been present throughout cosmic evolution, influencing quantum processes from the earliest moments after the Big Bang and helping to guide the universe's development toward greater complexity and awareness. The quantum nature of consciousness might also provide mechanisms for information transfer and processing that transcend classical limitations. Quantum entanglement could allow conscious beings to share information instantaneously across vast distances, while quantum superposition might enable forms of parallel processing impossible with classical neural networks. Advanced civilizations might develop technologies that exploit these quantum consciousness effects, creating collective intelligences that operate as single entities while maintaining multiple individual perspectives. These possibilities suggest that consciousness might play a fundamental role in cosmic evolution, not as a passive observer, but as an active participant in the universe's ongoing creation. The questions about what existed before the Big Bang might ultimately be answered by understanding the role of consciousness in quantum cosmology and recognizing that awareness itself might be one of the universe's most fundamental creative forces. Reality might be fundamentally computational, with everything we experience emerging from the processing of pure information according to mathematical rules that we interpret as physical laws. This digital physics perspective suggests that asking what came before the Big Bang is equivalent to asking what existed before a cosmic computer program began executing, opening entirely new approaches to understanding existence itself and the deepest nature of space, time, and matter. The it from bit hypothesis, proposed by John Wheeler, suggests that all physical quantities derive their meaning from binary choices, from information processing events that select specific outcomes from quantum mechanical possibilities. In this framework, particles, forces, and space-time itself would be emergent properties of underlying information processing, rather than fundamental constituents of reality. Every measurement, every interaction, every physical event would represent information processing operations in a vast cosmic computation that we experience as the unfolding of space and time. Information theory provides powerful tools for understanding physical processes across all scales, from quantum mechanics to black hole physics to cosmology. The holographic principle demonstrates that information can be encoded more efficiently than classical physics suggests, with three-dimensional volumes fully described by information on two-dimensional surfaces. Similarly, quantum error correction shows how information can be preserved even when individual physical systems are disrupted or destroyed, suggesting that information itself might be more fundamental and durable than the matter and energy that carry it. Black hole thermodynamics reveals deep connections between information, entropy, and gravity that point toward information's fundamental role in physics. The Bekenstein-Hawking entropy of a black hole is proportional to the area of its event horizon, not its volume, suggesting that the information content of any region of space is finite and bounded by the area of its boundary surface. This area law for information storage appears to be a fundamental principle that applies throughout the universe, not just to black holes. It implies that reality itself might be structured as information patterns distributed on cosmic boundaries rather than filling three-dimensional volumes as our intuition suggests. If reality is fundamentally informational, then the laws of physics would represent computational algorithms running on some kind of cosmic computer system. Gravity might be a subroutine that calculates how information patterns attract each other, while quantum mechanics might be the operating system that manages how information can be accessed and modified. The apparent fine-tuning of physical constants could reflect the fact that the universe is running software specifically designed to generate complexity and consciousness, with the constants representing carefully chosen parameters that optimize the program's ability to produce interesting and intricate structures. The simulation hypothesis represents one extreme version of digital physics, suggesting that our universe might be a computer simulation running on some vastly more powerful computational system. While this idea has captured popular imagination through movies and science fiction, it raises profound philosophical questions about the nature of simulated versus real experience. If consciousness can exist in any sufficiently complex information processing system, then the distinction between simulated and fundamental reality might be less meaningful than it initially appears. A conscious being implemented in software would experience genuine thoughts, feelings, and sensations regardless of the underlying computational substrate. Recent developments in theoretical physics support the idea that computation might be more fundamental than previously imagined. The ADS/CFT correspondence in string theory demonstrates that gravitational physics in higher dimensional space is exactly equivalent to quantum field theory computations on the boundary of that space. This isn't merely an analogy, but a precise mathematical duality where every gravitational calculation has a corresponding computational algorithm that produces identical results. Such dualities suggest that the distinction between computation and physics might be artificial, with both representing different perspectives on the same underlying informational processes. Quantum computation provides insights into how information processing might operate at the most fundamental levels of reality. Quantum computers can perform certain calculations exponentially faster than classical computers by exploiting quantum superposition and entanglement effects to process multiple possibilities simultaneously. If reality itself is computational, it might be essentially quantum computational, with the universe processing information in ways that transcend classical computational limits. The quantum nature of microscopic physics could be a direct reflection of the quantum informational processes that underlie all physical phenomena. The digital physics perspective offers revolutionary approaches to understanding cosmic origins. The Big Bang might represent the moment when a cosmic program began executing, transforming static information patterns into dynamic space-time evolution. Before this computational moment, the information that would become our universe might have existed as unexecuted code or as dormant data in some vast information processing system. Alternatively, our universe might be one sub-process in an enormous distributed computation, with countless other universes representing different computational tasks or parallel data processing operations running on the same cosmic hardware. Information conservation principles, fundamental to both physics and computation, suggest that all cosmic history is permanently encoded in reality's information structure. Every event, from quantum fluctuations to galaxy formation to the emergence of consciousness, might be preserved as information patterns that could theoretically be accessed by sufficiently advanced information processing systems. This cosmic information archive could serve as a kind of universal memory bank, preserving the complete history of everything that has ever occurred and making it potentially accessible to future intelligences with appropriate computational capabilities. The evolution of information processing capabilities represents one of the universe's most remarkable trends, progressing from simple chemical reactions to biological computation to technological artificial intelligence. If this trend continues, future information processing systems might achieve capabilities that seem impossible from our current perspective, potentially including the ability to manipulate reality's computational substrate directly or to access information from parallel computational processes running elsewhere in the cosmic computer system. Advanced civilizations might learn to reprogram reality itself, modifying the algorithms that we experience as physical laws. Claude Shannon's information theory demonstrates that any message can be encoded in binary form, reducing all possible information to sequences of yes, no choices. If reality is informational, then everything we experience, from the taste of coffee to the light of distant stars, would ultimately reduce to patterns of binary information processing. The richness and complexity we observe would emerge from the intricate organization and processing of these fundamental binary elements, much as complex computer programs emerge from simple binary operations. The relationship between information and energy becomes crucial in digital physics models. Landauer's principle establishes that erasing information requires a minimum amount of energy, connecting thermodynamics to computation. If the universe is computational, then the second law of thermodynamics might be a direct consequence of the computational processes that generate reality, with entropy increase corresponding to the irreversible consumption of computational resources as the cosmic program executes. Digital physics also provides new perspectives on the measurement problem in quantum mechanics. If reality is computational, then quantum measurement might represent information processing operations that convert superposition states into definite computational outputs. The probabilistic nature of quantum mechanics could reflect the underlying algorithmic processes that determine how quantum information gets processed into classical computational results. These ideas connect to consciousness through the recognition that brains are sophisticated biological computers, processing information through neural networks that bear striking resemblances to artificial computational systems. If consciousness emerges from information processing, as most neuroscientists believe, then digital physics suggests that conscious experience might be a natural feature of sufficiently complex computational systems, regardless of whether they're implemented in biological neural networks or silicon-based computers. Our universe appears to be exquisitely calibrated for the existence of complexity, life, and consciousness, with fundamental constants balanced so precisely that tiny changes would render atoms unstable, stars impossible, or chemistry forbidden entirely. This apparent fine-tuning raises profound questions about cosmic origins and the relationship between physical laws and the observers who discover them, challenging us to understand why reality seems so perfectly suited for the emergence of beings capable of contemplating their own existence. Consider the fundamental forces that govern reality with unprecedented precision. Gravity appears to be exactly the right strength to allow stars to form and shine for billions of years, creating the stable conditions necessary for planetary systems and biological evolution. If gravity were just slightly stronger, by even 1 part in 10 to the 40, stars would burn through their nuclear fuel too quickly, exhausting their energy supplies in millions rather than billions of years, never providing the extended time periods necessary for chemical evolution and biological complexity to develop. If gravity were correspondingly weaker, gas clouds in the early universe couldn't collapse under their own weight to form stars in the first place, leaving the cosmos cold, dark, and lifeless forever. The electromagnetic force demonstrates even more remarkable precision in its calibration for complexity. Its strength determines how tightly electrons bind to atomic nuclei, establishing the fundamental scale for atomic sizes, chemical bond energies, and molecular structures. Change electromagnetic force strength by just a few percent in either direction, and either atoms couldn't form stable configurations, or chemistry would be too unstable to support the complex molecules, like DNA, RNA, and proteins that form the basis for biological systems. The delicate balance between electromagnetic attraction and quantum mechanical repulsion that gives atoms their structure and stability appears to be calibrated with extraordinary precision. The strong nuclear force that binds protons and neutrons into atomic nuclei displays perhaps the most remarkable fine-tuning of all the fundamental interactions. A 5% change in either direction would eliminate either carbon or oxygen from the universe by making the nuclear fusion reactions that create these elements in stellar cores either impossible or too efficient. Without both carbon and oxygen, the rich chemistry that supports biological complexity becomes impossible, reducing the universe to simple hydrogen and helium with no possibility for complex molecular structures. The triple alpha process that creates carbon from helium nuclei in stellar cores requires such precise energy matching that physicist Fred Hoyle famously predicted its existence based purely on anthropic reasoning before experimental confirmation. Most dramatically, the cosmological constant that drives dark energy appears to be fine-tuned to an almost incomprehensible degree. Quantum field theory predicts this constant should be enormous, roughly 10 to the 120 times larger than observed values, causing space to expand so violently that matter could never clump together into stars, galaxies, or any complex structures. Instead, it has almost exactly the tiny positive value needed to allow cosmic structure formation while driving the observed accelerating expansion, differing from the theoretical prediction by 120 orders of magnitude in what represents perhaps the worst prediction in the history of physics. The probability of all these constants randomly falling within their life-permitting ranges is effectively zero, comparable to throwing a dart blindfolded from the distance of the Andromeda Galaxy and hitting a specific atom on Earth. This extraordinary precision has led to intensive efforts to understand whether there are deeper physical principles that could naturally explain apparent fine-tuning without invoking design or incredible coincidence. One approach invokes the anthropic principle, which comes in several versions with different philosophical implications. The weak anthropic principle simply notes that we necessarily observe a universe compatible with our existence, because incompatible universes couldn't produce observers capable of making observations. This reasoning becomes more compelling when combined with multiverse theories that predict vast numbers of universes with varying physical constants. Among infinite possibilities, some universes would randomly possess the right combinations of parameters for complexity, and these would be the only universes containing observers capable of noting the apparent fine-tuning. The strong anthropic principle goes further, suggesting that the universe must possess properties that make the development of intelligent life inevitable. This version implies that consciousness and intelligence represent fundamental features of cosmic evolution rather than accidental byproducts, raising questions about whether the universe possesses some inherent tendency toward complexity and awareness. However, anthropic reasoning remains highly controversial among physicists and philosophers. Critics argue that it's unscientific to invoke unobservable parallel universes to explain observed phenomena, and that anthropic arguments might discourage the search for deeper physical principles that could explain apparent fine-tuning through natural mechanisms rather than selection effects. The anthropic approach also faces the reference class problem. Among all possible observers, which types should we consider when evaluating anthropic probabilities? Alternative approaches seek physical mechanisms that could naturally produce fine-tuned constants without invoking multiverse selection effects. Some theories propose that fundamental constants aren't actually constant, but evolve to their current values through cosmic evolution processes. In these models, the constants we observe represent the stable endpoints of dynamical evolution rather than randomly chosen initial conditions. Other theories suggest that the constants are determined by the specific mechanism through which our universe formed from quantum vacuum fluctuations, with the formation process naturally selecting parameter values compatible with complexity. String theory offers another perspective on fine-tuning, suggesting that the apparent precision might be explained by the specific configuration of extra dimensions in our universe. the landscape of possible string theory solutions is enormous, potentially including 10 to the power of 500 different possible universes with different physical laws, particle properties, and fundamental constants. If all these possibilities are realized somewhere in a higher dimensional multiverse, fine-tuning becomes a natural consequence of observer selection among infinite alternatives, rather than evidence for design or incredible luck. Recent developments in quantum cosmology suggest even more radical possibilities. Some theories propose that consciousness itself might play a role in determining physical constants through quantum measurement effects. If the early universe existed in quantum superposition states containing different possible parameter values, the emergence of conscious observers might have retroactively selected the branch of cosmic history with constants compatible with consciousness. This would create a participatory universe where awareness helps determine the physical laws that govern reality. The fine-tuning problem also connects to deeper questions about cosmic purpose and meaning. Some argue that the apparent design of physical laws for complexity and consciousness suggests intentional creation by some form of cosmic intelligence, or represents evidence for deeper organizing principles in nature. Others maintain that any sufficiently complex universe would appear fine-tuned to its inhabitants, making the observation of fine-tuning inevitable rather than remarkable. Recent developments in effective field theory and the study of naturalness in particle physics have revealed that fine-tuning might be more common in physical theories than previously appreciated. Many successful theories in physics require precise relationships between different parameters to avoid pathological behaviors, suggesting that fine-tuning might be a generic feature of complex systems rather than evidence for special design. The multiverse approach to fine-tuning faces its own challenges, including the measure problem of how to assign probabilities to different types of observers in an infinite ensemble of universes. Different mathematical measures can lead to contradictory anthropic predictions, making it difficult to test multiverse explanations for fine-tuning scientifically. Some critics argue that invoking infinite unobservable universes to explain fine-tuning represents a retreat from empirical science into metaphysical speculation. Despite these debates, the fine-tuning problem continues to drive important research in fundamental physics and cosmology. Whether the solution involves multiverses, evolving constants, quantum consciousness effects, or entirely new physical principles, understanding fine-tuning remains central to comprehending why the universe possesses the specific properties that allow complex structures and conscious observers to exist. Understanding cosmic origins requires considering not just the past, but also the ultimate destiny of the universe, as the two might be more intimately connected than conventional thinking suggests. Current observations indicate our universe is dominated by dark energy, a mysterious component that drives accelerating expansion and will determine the cosmos's far future evolution over the next hundreds of billions of years. If dark energy remains constant, our universe faces heat death through eternal expansion. Over the next 100 billion years, cosmic expansion will carry distant galaxies beyond our observable horizon, leaving future observers in our local group with an increasingly isolated view of space. Star formation will peak within the next few billion years, then gradually decline as gas supplies are exhausted. Red dwarf stars, the most efficient nuclear furnaces, will continue shining for trillions of years, but eventually they too will fade. After stellar death, the universe will enter the black hole era, lasting from about 10 to the power of 40 to 10 to the power of 100 years after the Big Bang. During this period, black holes will be the dominant gravitating objects, slowly accreting remaining matter and energy. Even black holes aren't eternal, however, as they gradually evaporate through Hawking radiation, with evaporation time inversely proportional to mass. Stellar mass black holes will vanish after about 10 to the 67th power years, while supermassive black holes in galaxy centers will persist until about 10 to the 100th power years. The final era of cosmic evolution will be dominated by elementary particles drifting through exponentially expanding space, with occasional interactions becoming increasingly rare as expansion carries particles beyond each other's light horizons. The universe will approach maximum entropy, a state of perfect thermal equilibrium where no energy differences exist to drive any physical processes. However, this heat death scenario assumes that dark energy properties remain constant over cosmic time. Alternative possibilities could lead to dramatically different outcomes. If dark energy strengthens over time, expansion could accelerate so violently that it tears apart galaxies, stars, planets, and eventually atoms themselves in a Big Rip scenario, potentially occurring within 20 to 30 billion years. Conversely, if dark energy weakens or becomes repulsive, cosmic expansion could slow, stop, and reverse, leading to a big crunch where everything collapses back together in conditions similar to the Big Bang. This could set the stage for cyclic cosmology models where each big crunch becomes a new Big Bang, creating an eternally oscillating universe. Advanced civilizations might not be passive observers of cosmic fate, but could actively intervene in cosmic evolution. Sufficiently developed technology might learn to manipulate dark energy, create artificial black holes for energy storage, or even influence the fundamental structure of space-time itself. Freeman Dyson and other theorists have explored how intelligence might survive and thrive even under heat-death conditions by becoming increasingly efficient at information processing as available energy decreases. The possibility of cosmic engineering opens extraordinary scenarios for the far future. Advanced civilizations might create new universes through controlled vacuum decay or black hole formation, ensuring the continuation of complexity and consciousness beyond our current cosmic cycle. Such universe creation might represent the ultimate expression of intelligence, transforming advanced beings into cosmic gardeners who cultivate realities suited for consciousness and complexity. Information preservation represents another crucial consideration for cosmic destiny. If information cannot be destroyed, then everything that happens during cosmic evolution might be permanently encoded in the universe's structure, potentially allowing future intelligence to reconstruct complete histories of earlier cosmic epochs. This cosmic information storage could serve as a form of immortality for civilizations that learn to encode their essential information into the universe's permanent record. The connection between cosmic origins and ultimate fate becomes apparent in models where advanced consciousness in the far future influences the initial conditions that allowed consciousness to emerge. If quantum mechanics permits retroactive influences through observer effects, then the choices made by advanced civilizations could help determine the cosmic parameters that made their evolution possible, creating self-consistent causal loops that connect the universe's beginning and end. Understanding cosmic origins requires considering not just the past, but also the ultimate destiny of the universe, as the two might be more intimately connected than conventional thinking suggests. Current observations indicate our universe is dominated by dark energy, a mysterious component that drives accelerating expansion and will determine the cosmos's far future evolution over the next hundreds of billions of years. If dark energy remains constant, our universe faces heat death through eternal expansion. Over the next 100 billion years, cosmic expansion will carry distant galaxies beyond our observable horizon, leaving future observers in our local group with an increasingly isolated view of space. Star formation will peak within the next few billion years, then gradually decline as gas supplies are exhausted. Red dwarf stars, the most efficient nuclear furnaces, will continue shining for trillions of years, but eventually they too will fade. After stellar death, the universe will enter the black hole era, lasting from about 10 to the power of 40 to 10 to the power of 100 years after the Big Bang. During this period, black holes will be the dominant gravitating objects, slowly accreting remaining matter and energy. Even black holes aren't eternal, however, as they gradually evaporate through Hawking radiation, with evaporation time inversely proportional to mass. Stellar mass black holes will vanish after about 10 to the 67th power years, while supermassive black holes in galaxy centers will persist until about 10 to the 100th power years. The final era of cosmic evolution will be dominated by elementary particles drifting through exponentially expanding space, with occasional interactions becoming increasingly rare as expansion carries particles beyond each other's light horizons. The universe will approach maximum entropy, a state of perfect thermal equilibrium where no energy differences exist to drive any physical processes. However, this heat death scenario assumes that dark energy properties remain constant over cosmic time. Alternative possibilities could lead to dramatically different outcomes. If dark energy strengthens over time, expansion could accelerate so violently that it tears apart galaxies, stars, planets, and eventually atoms themselves in a Big Rip scenario, potentially occurring within 20 to 30 billion years. Conversely, if dark energy weakens or becomes repulsive, cosmic expansion could slow, stop, and reverse, leading to a big crunch where everything collapses back together in conditions similar to the Big Bang. This could set the stage for cyclic cosmology models where each big crunch becomes a new Big Bang, creating an eternally oscillating universe. Advanced civilizations might not be passive observers of cosmic fate, but could actively intervene in cosmic evolution. Sufficiently developed technology might learn to manipulate dark energy, create artificial black holes for energy storage, or even influence the fundamental structure of space-time itself. Freeman Dyson and other theorists have explored how intelligence might survive and thrive even under heat-death conditions by becoming increasingly efficient at information processing as available energy decreases. The possibility of cosmic engineering opens extraordinary scenarios for the far future. Advanced civilizations might create new universes through controlled vacuum decay or black hole formation, ensuring the continuation of complexity and consciousness beyond our current cosmic cycle. Such universe creation might represent the ultimate expression of intelligence, transforming advanced beings into cosmic gardeners who cultivate realities suited for consciousness and complexity. Information preservation represents another crucial consideration for cosmic destiny. If information cannot be destroyed, then everything that happens during cosmic evolution might be permanently encoded in the universe's structure, potentially allowing future intelligence to reconstruct complete histories of earlier cosmic epochs. This cosmic information storage could serve as a form of immortality for civilizations that learn to encode their essential information into the universe's permanent record. The connection between cosmic origins and ultimate fate becomes apparent in models where advanced consciousness in the far future influences the initial conditions that allowed consciousness to emerge. If quantum mechanics permits retroactive influences through observer effects, then the choices made by advanced civilizations could help determine the cosmic parameters that made their evolution possible, creating self-consistent causal loops that connect the universe's beginning and end. Some theories suggest that consciousness might be essential for cosmic evolution itself, with observer effects playing fundamental roles in determining which quantum possibilities become actualized. If true, then the death of all consciousness would represent not just a local tragedy, but a cosmic catastrophe that could undermine the reality of past events that led to consciousness. This creates strong incentives for consciousness preservation that might drive cosmic evolution toward outcomes that ensure the eternal continuation of awareness and intelligence. Our journey through the frontiers of cosmic origin theories reveals a universe far stranger and more wonderful than our ancestors could have imagined, yet also shows that the deepest questions about existence remain as mysterious as ever. We've explored quantum vacuum cosmology, where universes arise as fluctuations in an eternal quantum foam. We've examined eternal inflation, creating infinite multiverses of pocket universes. We've investigated cyclic cosmologies with endless cycles of expansion and contraction. We've delved into higher dimensional Brane cosmology, holographic reality, and the possible role of consciousness in cosmic evolution. Each of these approaches provides insights into what might have existed before the Big Bang, but none offers definitive answers to the ultimate questions about existence itself. Why does anything exist rather than nothing? Why do the laws of mathematics and logic themselves exist? Why does consciousness have the capacity to contemplate its own existence and the nature of reality? These questions point toward mysteries that may transcend physics itself, touching on the deepest philosophical problems about being, meaning, and purpose. Yet perhaps the persistence of these questions is itself significant. The fact that reality continues to surprise us, continues to reveal new depths of complexity and beauty, might be among its most remarkable features. We are not external observers of cosmic evolution, but integral participants in the universe's process of self-discovery. Modern cosmology reveals that we exist during an extraordinary epoch in cosmic history. We live after the formation of complex atoms, but before the death of stars, during the brief cosmic moment when intelligent life can emerge and contemplate the universe's origins and fate. We are made of elements forged in stellar cores, organized by biological evolution, and capable of mathematical reasoning that can probe the deepest structures of reality. The scientific enterprise itself represents one of the universe's most remarkable achievements. Through human consciousness and intelligence, the cosmos has developed the ability to study itself, to discover its own history, to probe its own fundamental principles. Every astronomical observation, every physics experiment, every mathematical theorem represents the universe exploring its own nature through conscious beings that have emerged from cosmic evolution. This participatory relationship between consciousness and cosmos suggests that the boundaries we typically draw between observer and observed, between mind and matter, between self and universe, may be less fundamental than they appear. Quantum mechanics hints at deep connections between measurement and reality. Information theory suggests that consciousness and computation might be more closely related than classical physics imagined. The holographic principle indicates that space itself might emerge from more fundamental information relationships. If consciousness plays an integral role in cosmic evolution, then the emergence of intelligence might not be an accidental byproduct of cosmic processes, but a natural outcome toward which the universe tends. The anthropic fine-tuning of physical constants could reflect not divine design or pure coincidence, but a deep connection between the structure of reality and the possibility of awareness itself. The questions we've explored about pre-Big Bang scenarios remain at the cutting edge of theoretical physics and cosmology. While we cannot definitively answer what existed before the Big Bang, the scientific process of investigating these questions continues to reveal new aspects of reality's structure and deepen our understanding of existence itself. Each theoretical framework we've examined, from quantum vacuum cosmology to eternal inflation to cyclic models, represents humanity's attempt to extend the boundaries of knowledge into previously inaccessible realms. Future observations and theoretical developments will undoubtedly refine, modify, or potentially revolutionize our understanding of cosmic origins. Next-generation telescopes will probe the cosmic microwave background with unprecedented precision, potentially revealing signatures of pre-Big Bang physics. Gravitational wave detectors might observe signals from cosmic events that occurred before our observable universe formed. Particle accelerator experiments could discover new physics that illuminates the quantum processes underlying cosmic evolution. Advanced civilizations elsewhere in the universe, if they exist, might already possess knowledge about cosmic origins that far exceeds our current understanding. The universe might contain intelligence that has been exploring these questions for billions of years, longer than human science has existed. Contact with such civilizations could revolutionize our understanding of reality's deepest structures and our place within cosmic evolution. Yet even as science advances and our knowledge expands, the fundamental mystery of existence seems to deepen rather than resolve. Each answer reveals new questions. Each solution opens new problems. Each step forward shows us how much further the path extends. This eternal character of the mystery might itself be telling us something profound about the nature of reality and consciousness. Perhaps the universe is structured in such a way that consciousness will always find new depths to explore, new questions to investigate, new mysteries to contemplate. The relationship between mind and cosmos might be inherently inexhaustible, with each level of understanding opening access to even deeper levels that were previously inconceivable. This would make the scientific exploration of existence not a process with a final destination, but an eternal journey of discovery. The questions about what existed before the Big Bang ultimately connect to the most fundamental questions about consciousness, meaning, and purpose. Are we conscious beings merely complex arrangements of atoms governed by impersonal physical laws? Or does consciousness represent something more fundamental, perhaps even essential to the structure of reality itself? These questions bridge science and philosophy, empirical investigation, and existential reflection. Modern physics suggests that reality is far stranger, more interconnected, and more fundamentally mysterious than our everyday experience indicates. Quantum mechanics reveals a universe where observation plays a crucial role in determining outcomes. Relativity shows that space and time are dynamic and malleable rather than fixed and absolute. Cosmology demonstrates that we exist within an almost incomprehensibly vast and ancient cosmic evolutionary process. The investigation of cosmic origins represents one of humanity's highest intellectual achievements, requiring the integration of advanced mathematics, sophisticated observational techniques, and profound theoretical insights. Yet it also represents one of our most fundamentally human activities, the drive to understand our place in the cosmos and the nature of existence itself. Every culture throughout human history has developed origin stories, and modern scientific cosmology continues this ancient tradition using the tools of mathematics and empirical observation. As we stand at the current frontier of knowledge about cosmic origins, we find ourselves in a position similar to early explorers standing at the edge of unknown continents. We can see tantalizing glimpses of new territories beyond our current understanding, but the full landscape remains to be mapped. The theoretical frameworks we've explored represent our best current maps of this unknown territory, but like all maps, they are simplified representations of a reality that is undoubtedly more complex and surprising than any single theoretical framework can capture. The journey toward understanding what existed before the Big Bang is also a journey toward understanding the deepest nature of consciousness, reality, and existence itself. Whether we find ultimate answers or discover that the mystery is eternal, we participate in the most magnificent adventure possible. The universe's quest to understand itself through the consciousness that has emerged from cosmic evolution. In contemplating these questions, we realize that we are not separate from the mystery we seek to understand. We are expressions of the cosmic processes we study, conscious patterns in the universal information structure, local concentrations of the awareness that pervades reality. The questions we ask about cosmic origins are ultimately questions about our own deepest nature and the source of our capacity for wonder, understanding, and conscious experience. The mystery continues, and we are privileged to be part of it. Every moment of consciousness, every scientific discovery, every flash of understanding represents the universe exploring its own infinite potential through the awareness that has crystallized within cosmic evolution. The greatest discovery might not be what existed before the Big Bang, but the recognition that consciousness itself is the universe's way of experiencing and understanding its own existence. Thank you for joining this exploration into the deepest questions about cosmic origins and the nature of reality itself. The journey toward understanding continues, and each of us participates in this cosmic adventure of consciousness, discovering the mysteries of existence. The questions remain open, the possibilities remain infinite, and the wonder continues to grow with each step we take toward understanding the magnificent cosmic story of which we are all part.